Today's lecture, we will continue on the traditional AC generator. And when we say the traditional AC generator, we mean three-phase synchronous generator. The motors or generators can be either DC or AC. So we will focus on AC. And on AC motors, AC generators, they can be either single phase or three phase. So we will take the three phase parts. Then in the three phase generators, there is also a special type which is synchronous or induction. So we will focus on the synchronous. So in summary, the machines can be either motor or generator, or we have several types like transformer, etc. But these are the main things. Then in generator, we can have DC or AC. And in AC, we can have single phase or three phase. Then in three phase, we can have induction or synchronous. So when we say the traditional AC generator, we mean synchronous, three-phase AC generator, three-phase synchronous generator, and all of them are AC. That's what we mean by traditional AC. So you can see there are several cases or several types of generators. But the most common used in generating the power, the most common that one used in power plants are the three-phase synchronous generator. Why synchronous? Synchronous because it's suitable for constant speed, constant frequency. Our grid frequency is 60 hertz, then synchronous is better. Why three-phase? Because the power lines are based on three-phase. Why AC? The power based on AC. And generator, of course, to convert mechanical energy into electrical energy. Okay? That's why the reason why this is the most common. Then, last lecture we discussed about the different types or different speeds, like electrical speed, mechanical speed. There was number of poles and different ways. So here, let's focus more about the speeds. So whenever you see N as a speed, we mean this is RPM, revolution per minute, while omega, the speed in radian per second. So both of them are the same speed, but different units. So when you say like the distance in inches or feet, it's the same distance. But you can say this in inches, feet, or centimeters, meters, etc. They are all the same thing. But here, in order to standardize our analysis, whenever we see the simple n, this means we are using the speed in RPM. Whenever we see the simple omega, this means radian per second. Just keep this in mind so we can avoid the confusion. Should I substitute RPM or should I substitute radian per second? This is based on the symbol. Okay? Then, how to make the conversion between radian per second, RPM? This is very important because we're going to need to use this a lot. So omega equal 2 pi over 60 times n, or n equals 60 over 2 pi times omega. You need to write down this expression in your note sheets so you can, because you're going to use it. We will use it a lot. Okay? You don't need to memorize it, but you need to write it. So here is just like the relationship in how to convert between omega to RPM and the vice versa. While in the synchronous, we have two types of speeds, as we discussed last lecture, depending on the number of poles. So there is something called electrical speed, there is mechanical speed. Electrical speed, which is basically related to the frequency, as we see in the table, related to the frequency, while mechanical speed related to the actual speed or the physical speed. So when there is a number of poles, or like different more than 2 pole pairs, then we can get a slower physical speed to maintain a 60 hertz frequency. As we discussed last lecture, in order to get 60 hertz, we need 3,600 RPM. While if we have 4-pole machine, we need to have 1,800. If we have 6-pole, 900, etc. So by increasing the number of poles, the required speed to maintain 60 Hertz frequency will be less. As a result, we can say, whenever we discuss about the frequency, well, let's use the speeds called electrical speed. We'll call it the flux speed or the air gap speed. That's air gap flux speed that's happening inside the motor. While the physical speed, which is the actual speed, then that's why we call it mechanical speed or the actual speed. So in order to make a shortcut to say, okay, is this simple electrical or mechanical? So as a result or as a shortcut, we used to say to make simple E. So here NE, and I can remove S, there is no need for S. So NE or omega E, we mean this electrical speed. So like the electrical speed in RPM or radian per second. And when we say NM or omega M, this is the speed in mechanical speed. Sometimes we can say NS omega S. So whenever you see M or S, it's the same. Whenever we see mechanical speed or synchronous speed, those are the same. Then how we can find each one? So NE, which is in RPM, equals frequency times 60. Frequency times 60. That's what we used to discuss last lecture. Then omega E, which is the like the speed in radian per second, which is the same as we know 2 pi times f. We know this, omega, angular frequency, 2 pi times f. And in generator, angular frequency is the same as the speed, but keep in mind this is the electrical speed. While the mechanical speed, which is the actual speed, we have Nm and omega m, sometimes we can say Ns or omega s, equal 2 over number of poles. Np means number of poles. It should be N sub p. So number of poles, then it will be times N electrical, or 2 over number of poles times omega electrical. Then we can get to a formula that's very famous, the actual speed 120 F over number of poles. This is very famous formula in synchronous generators or synchronous motors as well. The speed 120 times the frequency over number of poles. I think you might be familiar with this if you deal with the motor. I think this will not be new for you. 120 F over number of poles. So as a result, we can say that we have 2 types of speeds, which is electrical or mechanical. So NE omega E or NS omega S, or in other words NM omega M. So mechanical and the synchronous are the same, but electrical is different. So electrical and mechanical, they will not be the same. When those will be the same, if and only if number of poles equal to 2. So if number of poles equal to 2, therefore electrical will be equal to mechanical. This is the only case, which is, you can recall last lecture about the synchronous, when we discussed about the synchronous generator, we said that if the number of poles equal 2, in order to get a 60 Hertz frequency, we need to have 3,600 RPM as electrical, 3,600 RPM as mechanical. So to get 60 Hertz frequency, number of poles equal 2, we need to have electrical as 3,600 RPM, mechanical as 3,600 RPM. But we said when we have 4, number of poles equal 4, then an electrical will be the same, 3,600, no change about the electrical. What's changing is the actual or the mechanical, which is 3,600 divided by 2, then it will be 1,800 RPM. And so on. If it's 6, it will be 900, and so on. So keep in mind, we have 2 different speeds. How about omega and N? Omega and N, they are the same speed, but in different units. Radian per second or RPM. So in electrical engineering, when we do the electrical parts, we prefer to use the radian per second. While when we do the applications in mechanical engineering, or the units that make sense for us more than radian per second, which is the RPM. So when we say the speed is, for example, 300 radian per second, Okay, I can say 300 is larger than 100, but I don't have the physical meaning. But when I say the speed is 300 or 3000 RPM, then I can imagine 3000 revolutions per second. So whenever we deal with applications related to mechanical parts, mechanical engineering, we will use RPM. Whenever we talk about something related to electrical thing, we will use radian per second. Okay? So here's like the differences between mechanical and electrical. Any questions about the speeds? Okay, so here, let's go back to the notes. The previous notes, again, I think maybe I forgot to mention, it was worksheet number 12. This is the worksheet. It should be available on Canvas. Now, going back to the notes. So we have the speed, or we mentioned that when you have number of poles equal to, then mechanical equal to electrical. And mechanical. Okay? So number of poles machine, omega r, or in other words, I can say omega synchronous, or in other words, omega mechanical. They are the same. RPM equal revolution per second times 60, which is RPS. And which is this RPS, which is the frequency. So here, whenever we talk about the speed in RPM, this means we will write the simple n. While when we discuss radian per second, we will use the simple omega, which is the same table as we discussed before. But keep in mind, again, synchronous speed equal the same as the actual speed, which is in other words mechanical speed, then this is the same as the rotor speed. So we can say this synchronous speed omega s or ns, mechanical speed omega m nm, rotor speed omega r nr. All of them are equal to each other. Okay? So no matter whenever you see omega m, omega r, omega s, they are all will be the same if and only if we are in the synchronous. When we go to the induction, you will see some differences. But here just this is if and only if synchronous. So we have 4 names for the speed. Omega synchronous, mechanical, rotor, all of these 3 are the same. Then the other type, which is the electrical. So the only thing that's difference, or there is a difference or different from them, which is the electrical without including number of poles. Okay, let's see an example and try to do some analysis about it. So a large 500 megavolt ampere generator to be designed in a modern nuclear power plants in the United Kingdom. A steam turbine is chosen where it operates most efficiently at this speed, 1492. How many poles recommended for this design generator? So we have a generator in the UK, and we need to get a speed closer to 1492 RPM. So the question is, we need to determine the number of poles. How can we solve this thing, or which formula that we need to use? We have the speed given 1492 RPM. Now, is this actual speed? Is this synchronous speed or actual speed or electrical speed? What do you think? This is the mechanical, which is the actual speed. We can say an R or an M, whatever. Then we need to find the number of poles. Let's recall what's the equation that the speed equation that we have number of poles and related to RPM, since it's an RPM, which is we have the formula that I said, the famous formula, 120F over number of poles, right? We know N, then we can find number of poles if and only if we know F. What's the frequency? It's not given. Shall I assume it's 60 hertz? Okay. We can say if it's not given, then 60 hertz. But let's read the question a little bit. it says in the UK. UK, the frequency is 50 hertz. Okay? So we will use a frequency 50 hertz because it's in the UK. That's why I use it. Other than that, if there is no information, I will use 60 hertz. How to find number of poles? Number of poles equal 120 times the frequency over the speed in RPM. So let's substitute 120 times frequency 50 hertz divided by NR, which is 1492. Then, what's the value will be? Can you calculate it?
.021.
4.022. Okay, whatever, like 4.2. So, what do you think the number of poles? Do I need to say like it's 4.02? No. Recall that the number of poles is related to the magnets. So the magnets must be, or number of poles must be even and integer. Because for every north, there must be a south. And we cannot say half north, one south, or etc. So we will choose the closest even integer. So it will be 4. So recall, number of poles must be even, positive, of course, even integer. So if, for example, when you do your calculation, it's 3.5, the closest one is 4. If it is 4.5, the closest one is 4. Something like that. Okay? 5.5, the closest one is 6. So it must be even integer. If you find number of poles at 3, no, make it the closest one. Maybe you can make it 4. Okay? Again, number of poles must be even integer. Then we will say a number of poles equal to 4. So if let's calculate the actual speed after choosing number of poles. 120 F50 divided by number of poles 4. So the answer will be 1500 RPM. So we will say that 1500 RPM very close to 1492. Close to 1492 RPM. Okay, any question? Okay. Let's talk more about the calculation of the synchronous generator. Recall this graph, which is we need to model this into an equivalent circuit. And we will assume this is balanced. We will assume this is it's 3-phase and balanced. So therefore, as we discussed in 3-phase, we will find the per phase equivalent circuit, right? Converting 3-phase to single phase. That's what we've learned before. Is this correct? Okay. By converting 3-phase into single phase, by picking up phase A as a reference, so phase A will be with angle 0, then this yields to be, we can draw an equivalent circuit, which is one part of the circuit. Then since in this generator, we have like stator and the rotor. Rotor is the magnets. Stator, which is this is stator. Call it stator. While the rotor is the magnets. So the stator based on coils, and whereas the electrical energy will be produced in these coils. Coil A, coil B, coil C. Coil means like inductance. So there will be a number of turns around the core. This is called inductance. And there is an equivalent circuit for it. The equivalent circuit for the coils, it will be based on the inductor. And in addition to that, there is an internal resistance. So the stator equivalent circuit will be based on resistor and inductor. Okay? Does this make sense? Resistor and inductor because there are number of turns. Then the rotor parts, we need to model the rotor. The rotor parts, which is rotating, whereas the electromagnetic field is induced and there is a movement. When there is a moving, according to Faraday's law, there will be a power generation. So the power will be generated at the rotor, right? As that's what we discussed last lecture. So since there will be a power generated there, we can model this as a voltage source. As a result, we can go to the model equivalent circuits for the generator, which is a voltage source, and this thing we call EF, or in other words, electromotive force. Then we have JXD, RA. Those are related to the stator. So those are the stator, while electromotive force is the rotor. Right? Stator, rotor. That's what we have in the equivalent model of the generators. Then the terminals of the generator, this is AN. Again, this is the per phase equivalent circuits, which is by picking up phase A as a reference. So inside this box, I call it generator because this is what the generator will be connected to the electrical grid. Okay? Again, we have the stator equivalent circuit, resistance and inductance. Why? We have turns around a sorted coil. We have coils and turns, number of turns around it. And whenever there is a number of turns around a certain element, they will make it an inductor. And this, therefore, also, in addition to this, there is an internal resistance for that. So we have inductance and resistance. The rotor is the rotating part, electromotive force, then it will be as voltage source. Then we need to connect this or hook it up to the grid. The grid can be the whole, for example, Auburn University electrical system. So how can we simplify it? Can we model the electrical grid, or do we need to write everything? We can model it by a simple model, which is voltage source, resistor, and voltage source and the series resistor. Why we get this model for the grid? Any thoughts? How we get this? I mean, VG, RG, JXG, this is an equivalent circuit for the grid, which is the whole of Auburn, as an example, Auburn University, or all of whatever I connected it to, whole city or whole state, as an example. What's this VG and RG, JXG? Where does this come from? Any thoughts?
The line?
Yeah, but I mean, this is an equivalent circuit. This is an RG, JXG. This is not actually the real life, I mean, not existing system. This is an equivalence. How we get this? Okay, have you ever heard of Thevenin's? Yes. So basically, this is the equivalent circuit or the Thevenin's model of the whole system. So basically, I mean, we will not use it here, but I would say like we found this by finding an Thevenin's equivalent circuits. So let's assume this generator is connected to Auburn University electrical system connection. So we modeled all of the Auburn University electrical system connection by a voltage source, and in DC we used to say a series resistor. Now, since we are in AC, it will not only be a series resistor, it will be a series impedance. And that impedance most likely will be based on resistor and inductance, because the vast majorities of the loads are based on motors. And motors, the equivalent circuit of them are inductors. That's why we have resistors and inductors, because again, the vast majorities of the loads are based on motors. Motors like used in AC, air conditioning, used in water heating, used in any like every or the vast majority for the devices that are consuming energy are based on motors. So as a result, the grid that we see here, this is Thevenin's equivalent circuit. Now, this yield to be, when we connect the generator into the grid, this is the overall equivalent circuit for phase A, per phase equivalent A, per phase equivalent circuit. So if we have phase B will be the same, but just write B, phase C will be the same. So we will repeat the same thing. But we don't need, we will assume it's balanced, so let's take phase A as a reference and that's it. Then by looking at this circuit, we will make some assumptions, like if the grid is assumed strong grid. What do I mean by strong grid? More robust grid. In other words, the grid that will not be affected by slight variations. So there is some definitions, we call it strong grid, there is weak grid. So strong grid, when there is any short circuit going on, it will not be affected. It can handle it. I mean, the circuit breaker will trip, it will not be affected. If there is any, for example, renewable energy fluctuation into the grid, it will not be impacted. So it looks like it's more robust. Whenever there is any change, it will not be affected. It will be just slightly affected. While there is a weak grid, when there is any variation, it will be affected. Sometimes it can affect on the stability. So the more events that we will have, like some events like fault analysis, short circuit analysis, this will try to weaken the grid more and more and more, weaken it more and more and more. While if the grid is healthy, it will be strong grid. So we will assume in our analysis, in the normal situation, everything it will be strong grid. That's the normal situation. That's what's supposed to be. If the grid is strong, we can say RG and JXG, these two can be negligible regarding to the impedance and the resistance of the generator. So Thevenin's equivalent circuits will be impedance and voltage source. The impedance can be close to zero if and only if it's strong grid, which means it will not be impacted by any other things. So anyway, under strong grid, we can neglect RG and JXG. The other assumption that we can do, if the generator is well designed and the number of turns tights well and it has been designed in the good way, then the internal resistance can be negligible, can be very, very small. Then the only element that we will have is JXD. And most likely, since I have I can buy the generator, I can choose the most efficient generator or the generators that we'll design. So we will assume the generator is well designed, we will assume the grid is balanced, and the same thing, we will assume the grid is strong. So this means the grid can be negligible, the resistance of the grid can be negligible as well. So as a result, we can remove this and remove this. This yields to have only JXD. That's the only element that we will have. So that's the circuits. That's the simplified circuits. And I can say this is the generator. And this is the grid. Then VA, which are the terminals of the generator. Keep in mind, JXD and EF are equivalent circuits. I cannot say, this is the terminals, just JXD, this is EF. I cannot find them, everyone alone. They are just inside the box, and that's what's inside the box, equivalent circuit of the box. Then again, the terminals A and B. So this is the physical connection here. And this equivalent circuit is not 100% true. Again, why? Because I neglected RA, I neglected Z grid. I assumed them very small, so they are negligible. So this leads to accuracy in 90s, not 100%, but in 90s. We can say 95 is acceptable. Then that's fine. If you need higher accuracy, if you are really matters with the application of the accuracy, then you need to use the original model. So that's why we use some, for example, when we deal with these generators, if we are dealing with some studies like nuts that does not require a higher accuracy, then we can use this simple model. If we need a great or better accuracy, then we need to use even modern model that's more complicated than this, which is called the transient model, And this one is, of course, this will be very complicated, and this is not our scope. This is most likely for a grad level course. Even for the undergrad in electrical engineering, this is very hard for them. This is for grad level, which is what's the transient model of the generators. And the analysis of that one will not be easy in handwritten, so you need to use the softwares in dealing with this, because there will be a lot of differential equations. Anyway, this is the simplest way. This is the simplest model, and again, the accuracy in 90s, 95% accuracy. It's not 100% the truth, but the reality, which was we have, but it's very close. And we say, okay, we can save more time by using this without the need to have that's better accuracy. I mean, that's 100% accuracy. So when there is any analysis, like we need to solve the equivalence or to solve the three-phase synchronous generator, the first step, you need to simplify or to draw down the equivalent circuits of the generator. So step number one, whenever you see any question solve with the synchronous generator, draw the equivalent circuit, which is this one. That's the equivalent circuit that we will use. We will not use that one. This is one before simplification. We will use the simplest one. So we'll use this. Okay? Now, how is the question of the generators will be? Basically, when you look at these circuits, we need to find, or when you deal any generators, you will draw down the equivalent circuits, then solve it based on the equivalent circuits. That's it. Let's look at this example, then see. Most likely, the equivalent circuit will not be given to you. So it's your job, please make sure when you have your note sheet, draw the equivalent circuit in your note sheet. Write the equivalent circuit in your note sheet. Then when you see it in the test or the quiz, you can just look at the note sheet and copy it, okay? Again, there will be a question in the exam, part number 1, draw the equivalent circuits. It will be 5 points. So the exam is out of 100. I already told you the 5 points. Draw the equivalent circuit, which is this one. Please make sure to write it in your note sheet. This is not only about the exam, this is only about how to answer the question, because if you didn't draw the equivalent circuit, you will get lost. Okay, let's see this question. A 100 megavolt ampere, 15 kilovolts, 60 hertz generator with XD 2.5, operated at rated condition and 0.866 lagging power factor. Determine the voltages and currents in the circuits. Here, it's very important to notice that we have rated value, and rated value, we will not use this every time. Rated value, this generator has been designed on a specific thing. These are the specifications. But, for example, when you buy a car, you can say this car can handle up to 150 miles per hour. Does this mean that you are driving every time you are driving at 150 miles? No, depending on your current operating condition. Therefore, make sure when you do your analysis, look at operates at what value. So here in this question, it operates at rated condition. So what we will do basically, let's try to simplify the question by writing down the values. We have JXD here 2.5, J 2.5. Then we have 15 kilovolts ampere. So kilovolts, because it's operated at the rated. Therefore, I'm going to use the rated values. So as a result, we can say V line to line equal 15 kilovolts. Remember this value, it's three-phase. So we can say V line to neutral equal V line to line over root 3. Then it will be 15 divided by root 3. It will be 7 points, or 8.66. 8.66 kilovolts. This is V line to neutral. How to find VA? We can say VAN using the famous formula. We have done this many times. So we will keep doing it, which is 8.66 angle 0 degrees kilovolts. Keep in mind kilovolt, which is times 10 power 3. That's VAN. Now we just calculated VAN. We know JXD, which is we know VA. How to find EF? and how to find IA. So the question is, let's see, we need to determine the voltages and the currents in this circuit. So we need to find IA and EF. We know VA. How to find IA, how to find EF? Someone can say, let's do KVL. If we do KVL, start from the left bottom corner, travel clockwise, EF plus IA JXD plus VA equals to 0. Therefore, EF will be IA JXD plus VA. Now, do you know JXD? Yes. Do we know VA? Yes. Do we know IA? No. Do we know EF? No. We have two unknowns. Okay, how can I find these two unknowns, or how can I do other analysis? Look at the other given information. It operates at rated, which is operates at 0.866 lagging power factor, 100 megavolts ampere. So it operates at 100 megavolts ampere, 0.866 lagging power factor. Now we can use this to find the power. What do we know about the power? S, is this the single phase or three phase power? Three phase, because there is no information about it, or there's nothing say this is the single phase, then the default is three phase. So we can say the power three phase equal S angle cosine inverse of power factor. It can be plus or minus if it's leading or lagging. Now, 100 megavolt ampere, is this real reactive appearance? Volt ampere? Appearance, right? So it will be 100 times 10 power 6 angle positive cosine inverse of 0.866. Why I make it positive? Because it's lagging. So we are using the circuit techniques that we've learned before. Then it will be 30 degrees. So it will be 100 times 10 power 6 angle 30 degrees. This is the three phase. Now, let's calculate the single phase, because we're for phase A. For phase A, which is the power of single phase, will be the power of three phase divided by 3. So it will be as 33.33 angle 30 degrees times 10 power 6 volt amperes. This is the power of single phase. Now we can take this benefits. We know the power, we know the voltage, we know VA, we know SA. So we can find the current easy, because we know SA equals VA times IA conjugates. As a result, IA will be SA over VA, all of them conjugates. So it will be 33 times 33, or 33.33 times 10 power 6, angle 30 degrees divided by 8.66 times 10 power 3, angle 0 degrees, all of it conjugates. So let's do the math first, then do the conjugate at the end. It will be 3.85 times 10 power 3, angle 30 degrees conjugate. Don't forget the conjugate. So let's do the conjugates at the end. 3.85 times 10 power 3, angle negative 30 degrees amperes. This is IA. Now I calculated IA. So I can substitute this in KVL equation. Recall the KVL equation that we wrote before, which is EF equals to IA JXD plus VA. So we just calculated IA JXD, which is 3.85 times 10 power 3, angle negative 30 degrees, times JXD, which is J2.5, plus VA, which is 8.66 times 10 power 3, angle 0 degrees. Then, to calculate the EF will be 15.84, angle 31.74 degrees, and times 10 power 3 volts. Or in other words, sometimes we can say in kilovolts, 15.84, angle 31.74 degrees, kilovolts. This is EF. So this is just circuit techniques. What I did, I just draw the equivalent circuits then it is circuit analysis. Three-phase circuit analysis. Divide the power by 3, and we know the power, we know the voltage, we can find the currents. How to find the source? Just do the KVL. Okay, does this make sense? Let me give you a few seconds to write, then we will go for the power transfer to the grid. Okay, so the power transfer to the grid, we know S, as we discussed, V times IA conjugates. Now, according to KVL, so KVL EF plus JXD, IA JXD, plus VA equal to 0. Therefore, we can say IA equals to EF minus VA, all of them divided by JXD. So, what I'm going to do, I'm going to substitute this here. So this yields to this equation. So EF, VA times EF minus VA over JXD, which will make it VA angle 0 by substituting EF, which is EF angle delta. So we use angle delta for EF. Minus VA angle 0. Why VA angle 0? Because we used to pick up phase A as a reference. Then EF, it's not necessarily to be angle 0, it can be with different things, so it will be EF angle delta. So we use the simple delta. So after doing simplifications, it will be converting this to rectangular coordinates. It will be EF VA over XD sine delta plus J EF VA over XD cosine delta minus VA square JXD. And we know this is PA plus JQA, because the complex power will be real power plus J imaginary part. So this yields, this is the real parts, this is the reactive part. Then the real power will be EFVA over JXD over XD without J sine delta, while QA will be EFVA XD cosine delta minus VA square over XD. And if we need to calculate the power in three-phase, power three-phase will be 3 times power phase A, then reactive power three-phase will be 3 times reactive power phase A. So if you need to calculate the complex power, you can either calculate the currents, then you see V times IA conjugates, this is method number 1, or method number 2, you can use these two formulas. Find the real power, find the reactive power. So method number 1, it looks like easier. So just let me say S VA times IA conjugate, and that's it. That's all. That's all what I need. Yes, that was easier in analysis. But what's the point of using method number 2? So basically, in method number 1, when we do the calculation, every time we need to calculate the currents. Let's change the load. The voltage is fixed. The current, we need to make some calculations. And the current will be EF minus VA over JXD, which requires more complications. While here, we don't need to do the current calculation. So the good point about method number 2, there is no need to do the current calculation. So we are using this in software or in many things, in many analyses, by taking the advantages, which is there is no need to use the currents. So as a result, we can say EFVA over XD sine delta. So again, if you use method number 1, method 2, they should give the same answer. There's no problem with that. And you can notice this when you look at the real power. You will see that EF is fixed most likely, VA is fixed, XD is fixed, right? VA is the voltage fixed, XD is the material of it which is fixed. EF, the electromotive force, most likely will be fixed. The only changing parameter is delta. So this yields to be, we can say PA will be constants times sine delta. Okay, how this looks like. Since it is, here is delta, here is the power, then the power will look like this way. The maximum power achieved when delta equal 90 degrees. Okay? Because sine of 90 degrees will be 1. So what's happening in real life? How the generator, how we can we control the amount of power being generated by the generator? By controlling delta. If we make delta 45, we can reduce it more. If we need to increase it, increase delta. So there is basically, you can say that in order to increase the amount of power being generated, we can control delta. That's how you can imagine that's how we can control the amount of power being generated. Okay? Now, if we need to determine all of the complex powers in the previous example, basically the previous example, we said SA equal VA times IA conjugates, and it was 33.33 times 10 power negative, 10 power 6 angle 30 degrees. And we can convert this into rectangular coordinates, 28.87 times 10 power 6 plus J 16.67 times 10 power 6. That was for phase A. While when we discuss about the three-phase power, was 100 times 10 power 6, angle 30 degrees. So in rectangular coordinate, again, this is P plus JQ, PA plus JQA. This one will be 8.66, 86, I'm sorry, 0.6 times 10 power 6 plus J 15 times 10 power 6, which is, this is the power, real power 3-phase. This is the reactive power 3-phase. This is using method number 1. However, if you need to use method number 2, you can say PA equals to EF VA as a magnitude divided by XD sine delta. Then you can say P 3-phase will be 3 times PA. Then the reactive power, which is EF VA over XD cosine delta minus VA square over XD. Is it VA square over XD? Yes. And then to find Q 3-phase will be 3 times QA. Then you can substitute it. So this is method number 2, and we have method number 1 before. And of course, they should give the same answers. Again, recall that VA equals to 8.66 angle 0 degrees. EF equals to be, what was EF? 15.84, angle 31.74 degrees, and here's times 10 power 3, times 10 power 3. So we can say this is EF alone, this is delta. Okay? And the last notice, which is delta is positive if generator. Delta every time must be positive. If we discuss the motor, it will be negative. But if it is positive, it will be for the generation mode. Yeah, this is the end of the generator. Any question?